In part 3 of Introduction to Experimental Research, I want to examine hypothesis testing, what that means, and how we conduct hypothesis testing in research studies. Before that, though, I want to pick up where we left off, where we were talking about the study that we've read related to foam rolling using either a vibrating or a non-vibrating foam roller and its effects on various measures of recovery. And I left you with a number of questions, and I would like to see what your responses are here. So, using this quick quiz, what I would like you to do are to answer the questions listed on this slide. What were the independent variables? What were the dependent variables? What was the design? Was it a between subjects design or the within subjects design? And then how often were the measurements taken? The quiz that you're going to take is not graded, but I do want to use it as a way to assess whether you're learning, whether you understand the concepts that we've covered. Don't worry if you get answers wrong, you'll actually be given the correct answer after you enter your answer, but it's just a way for me to kind of see that you're participating and engaged in the content that we're learning. Well, thanks for taking the time to read the article and answer those questions. Here are the correct answers when it comes to the article that we read. And basically what we find, the independent variables for this article was treatment condition. And the treatment condition had two levels, right? Meaning that there were two different types of treatment conditions, one being the vibrating foam roller, one being the non-vibrating foam roller. The dependent variables, that's what we're looking to see what is affected, right? So the independent variable is the grouping variable, or what we're kind of manipulating. The dependent variable is what we're measuring to see if it's affected by changes in the independent variable. So the cause is the independent variable, the effect is the dependent variable. And they had a lot of dependent variables. Their primary measure was pain, measured by a visual analog scale during passive, nothing, during a quad contraction, during a squat, and during a quad stretch. So pain measured 4 different times. And then they also measured, they said these were secondary dependent variables or secondary measures: pain pressure threshold, muscle oxygen saturation, counter movement jump, and range of motion, both passive and active hip extension and knee flexion. So those were the dependent variables, and they looked to see if any of them were affected by the different foam roller types. And then the study was a between subjects design, because they started out with a large group of people and split them in half, with half doing the vibrating foam roller and half doing the non-vibrating foam roller. So that's a between subjects design. And then finally, how often were the measurements taken? They took the measurements 3 times. They took the measurements before the people did the eccentric training, the delayed onset muscle soreness training. So they took them at a baseline. They then took them when they were, after the DOMS treatment, but before they did the foam rolling. So they looked at, in the sore condition, what were their measures, and that was called the pre-treatment measure. And then they took one after the foam rolling, which is called the post-treatment measures. And primarily they were comparing the pre-treatment and the post-treatment to one another. They did compare the baseline to the pre-treatment to make sure that their eccentric training was significant enough to cause alterations. But really what we were looking at was the pre-treatment to the post-treatment numbers. All right, well, so then what is hypothesis testing? I mentioned what it is already. It's a guess. It's a statement or a guess at how an independent variable may impact a dependent variable. Guess isn't the best probably word to use because it's an educated guess. It's based upon the research that the researcher has or research team has already read. So it's a educated guess based upon other studies that were maybe close to the same, similar populations, maybe similar measures or something. But a hypothesis is a statement at how an independent variable, which could be a treatment or a training technique, may impact a dependent variable, which is usually some measure of performance or health or wellness, such as weight, 40-yard dash speed, vertical jump height, etc. Testing a hypothesis is what a research study will do. The researcher makes the guess, then tests the guess by collecting data, utilizing subjects, and so on. Then we see if those results are statistically significant. So testing a hypothesis allows us to examine the probability that differences or changes in a measure are due to the treatment or just due to random variability. So that probability is called a p-value. I don't want to overwhelm everybody with statistics here, but a basic understanding of statistics is really key to understanding the results of these types of studies. So when we test a hypothesis, we get a p-value typically. Most statistical tests are going to report a p-value, and they tell us the confidence that we can have in the data that we've discovered, and how confident can we be that those differences in the measures or changes in the measures are due to our treatment and not due to random variation in measurement. So for example, if I was to today have everybody come to my lab and jump as high as you can and measure how high you can jump using a vertex or using a force platform, right? We would find what your jump height is today. If I have you come back tomorrow and do the same exact thing, there's a very good chance your jump height would be slightly different tomorrow than it was today. Is that because there's anything different about you tomorrow? No, probably not. It's just due to random variability in the measure. We always kind of jump a little bit higher, a little bit lower, but it varies from day to day. When we do an experiment, when I maybe have you do a jump today and a jump tomorrow, but I do a treatment each day. One day I just have you jump, and that's the control treatment or control group. The second day you come back and I have you jump, but before you jump I have you do some static stretching. If I want to know if those differences from day 1 to day 2 are due to random variability in the measure or if they're due to the actual treatment, then I have to use statistics. And when I use statistics, what I'm going to get is a p-value. So I have to decide how confident I want to be that the differences are real and due to the treatment, or are they due to random variability? And that's what hypothesis testing allows us to do. So if we look at this statement here, does cryotherapy treatment immediately following a downhill sprint yield an improvement in hip and knee range of motion when compared to no treatment 24 and 48 hours post-run? That would be an example of a hypothesis. I'm making a guess, or I want to see, does cryotherapy treatment alter performance, in this case, range of motion performance, after doing a task that should make me very sore and potentially very stiff? So that's a hypothesis. I'm making a guess that cryotherapy treatment will change or improve my range of motion when compared to not doing cryotherapy treatment, both 48 and 24 hours after doing this eccentric loading of the quadriceps. So that's a hypothesis. And then I can test that hypothesis by measuring range of motion before the activity, after the treatment, and so on. And that can give me some insight as to whether or not this treatment has a real effect, a beneficial effect for my clients, my athletes, and so on. A good quality study will make the hypotheses very obvious, even though they may not specifically, explicitly state this is our hypothesis. In the study that we've read for this assignment, or for this presentation, the examining foam roller types, what were their hypotheses? Looking at their study, you've identified their variables and so on, but what specifically was their hypothesis? Well, really, they had multiple hypotheses, right? Because they studied several different things. They said their primary study, though, was looking at foam rolling, vibration versus non-vibration foam roller, will affect pain or decrease pain when compared to, again, the two foam rollers, and looking at after they've induced muscle damage. So I would say, even though they don't explicitly state it, that their hypothesis, their primary hypothesis, is vibration foam rolling will yield decreased pain when compared to non-vibration foam rolling after exercise with induced muscle damage. So the hypothesis clearly states the independent variable, which are the two foam rolling types, and the dependent variable, which is pain. They also had secondary hypotheses. They measured a bunch of different things, right? And those would be in either all separate hypotheses, or you could lump them together into one, which would be stated something like vibration foam rolling will yield improvement in pain pressure threshold, oxygen saturation, range of motion, and counter movement jump when compared to non-vibration foam rolling after exercise with induced muscle damage. The induced muscle damage isn't a variable, but it is a condition that's very important to understand this study. So I would still throw that into the hypothesis because it's important for the reader to understand. But again, the hypothesis defines the variables and says, what are we looking at? What are we examining? And typically gives a best guess from the researcher as to maybe the directionality, increase or decrease, improve or worsen in terms of what the effect may be. So hypothesis testing starts with writing a hypothesis and then testing it through an experiment. Once the data is collected, we then do a statistical analysis to see if the differences in the dependent variable, the differences in the measures, are real and due to the treatment, or are they potentially just due to random variability. To do that, typically threshold p-values, how confident we want to be, are typically set before the study begins. The threshold p-value, in order to say that I am going to accept the hypothesis, I'm going to say that the hypothesis is true based upon the data, is called the alpha. And again, this is just the Greek letter for alpha. This is the threshold statistical significance we're looking at. Typically, we see numbers like 0.05 or 0.01. Suffice it to say, when we see an alpha set at 0.05, it's basically saying that we want to be 95% confident that the difference is due to our treatment. We're willing to take a 5%, that's what the 0.05%, chance of being wrong, but we want to be 95% confident that we're correct. If the researchers choose an alpha of 0.01, that means they are willing to take a 1% chance of being wrong, or they want to be 95% confident that the treatment had an effect. When you look at studies in our field, wellness and fitness and so on, we typically see a 0.05 set as the alpha. If you look at studies, maybe looking at more serious implications, drug studies looking at the effect of a drug on improving outcomes for patients, they don't want to take as big of a chance of being wrong. So you'll see alphas set instead of at 0.05 or 5%. They'll set at 0.01 or 1% or even 0.001, which is 0.1%. So again, but typically the alpha in our field is going to be set at 0.05. And again, what that means is we're willing to take a 5% chance of being wrong, and we want to be 95% confident that if we say the treatment works, that it truly does work. Testing a hypothesis uses interferential statistics, also known as tests of significance. So again, what we're looking to see is if differences in the measures are true or real, statistically significant, or are they just due to random variability? There are different tests that will give us the ability to test statistical significance. In the literature, in our field especially, we often see t-tests used, ANOVAs used, or MANOVAs used. But they all do basically the same thing. They examine the differences in two measures or more and see if they are due to random chance or are they actual differences. And again, a t-test is typically used when we have two groups where we're looking at the results. An ANOVA is typically used, or an analysis of variance is used when there's more than two groups. And then a MANOVA is a multiple analysis of variance, which means that we have multiple dependent variables that are being studied. All of these, though, I don't expect you to become statistical experts. We'll be talking about these and seeing examples of these as we move forward. But all of these are going to give us a p-value. So basically, if I did my study where I put people on a 6-week-long training program, 2 different training programs, and I wanted to compare the results, what would happen is I would get differences in their performance, right? I would have, some people get faster, some maybe get slower, some get way faster, some a little bit faster. But in the end, I take all of my subjects and I look at their mean improvement. If one group, the regular training group, improved their 5K time by 1 minute, and the other group, the HIT group, improved their 5K time by 2 minutes, I would say, hey, that's a big difference. A 1 minute drop in a 5K is very significant, right? Especially if they're already pretty fast. But I don't know if that difference is just due to random variability in the measure or due to my treatment. If I run a statistical test, such as a t-test, and my p-value comes out as 0.03, okay, my p-value comes out as 0.03, that's less than my alpha, which is 0.05. That means that I say this difference between the treatment tests, or the treatment programs, the exercise programs, is real. It's likely to be true. It's likely that the HIT training program is better than the traditional training program. And that's because the p-value is less than 0.05. So hypothesis testing gives us confidence in the differences that we see in studies potentially. Regardless of our best efforts, errors can be made in statistical testing. Errors can be made in the conclusions that we make about our data or about the data in a study. So it's important for you to know what this error means, because we do have to, when we read these different studies, we have to take it with a grain of salt that they could have made the wrong conclusion. As I said, if we are testing a hypothesis and we use a statistical test and we've set an alpha at 0.05, then what we're really trying to do is make sure that we're 95% confident that the difference is real and only a 5% chance of being wrong. That is called errors. Those are called statistical errors. And statistical testing, basically, in statistical testing, we are weighing a hypothesis against what's called a null hypothesis. So, and then with our testing, we're seeing which hypothesis we should accept. The hypothesis that we've created or the null hypothesis, which is basically the opposite hypothesis. The null hypothesis typically states that there is no difference between the groups following the intervention, versus our hypothesis, our experimental hypothesis, typically says that there is going to be a difference based upon our treatment. So with all of this, the null hypothesis and the research hypothesis, there's still a chance of making errors in our conclusions. But at least we know what the chances of those errors are. We can't ever be 100% confident that this treatment is better than that treatment. But we can be very confident. We can be 95% confident if we find the right test results. So that's what, again, hypothesis testing allows us to do. So let's look at an example here. On the right of this slide, I have a hypothesis saying there will be a greater increase in hip flexion range of motion following foam rolling with a vibrating foam roller when compared to foam rolling with a non-vibrating foam roller in individuals with delayed onset muscle soreness. So that's the research hypothesis, very similar to the study that we've been reading, right? It says there's going to be a increase in both measures, both foam rollers, but a greater increase for the vibrating foam roller. The null hypothesis that would go along with that hypothesis is saying there will be no difference in hip flexion range of motion following foam rolling with a vibrating roller when compared to foam rolling with a non-vibrating foam roller in individuals with DOMS. So those are the opposite. So in reality, one of those two is true. Either foam rolling does, with a vibrating foam roller, does yield an increased range of motion, or it doesn't. So with our study, we're trying to figure out which of these hypotheses is true, the null hypothesis or the research hypothesis. That brings me to the concept of errors, right? So what we're doing with hypothesis testing is trying to limit the chance of making an error by setting the p-value, the alpha value at a specific level. So let's talk a little bit about statistical errors. Again, just conceptually, this is helpful for us. So let's look at two things here. What we have is the truth. If we were to test the entire population of athletes with these foam rollers, what would we find? Is there a difference between the foam rollers? So this is what really exists. Okay? Either the treatment has no effect or the treatment has a real effect, a positive effect. Okay? So that's the truth. That's what really exists. And we're trying to find the truth with our research. With our research, we don't test the whole population. We collect data from a sample, which is a subgroup of the population. So based upon the data you collect and then analyze, this is the conclusion we make. Okay? Let's say in real life the treatment has no effect. So this is the truth. If we see no difference due to the treatment, so if we measure people with both foam rollers, their range of motions are pretty much close together, very similar, we conclude then that there's no difference due to the treatment. That means we have not made an error. We're correct, right? We have decided there's no effect, and in reality there's no effect. Sometimes, however, though, there's a chance of making an error where we say there is no difference, but in reality there is a difference. That's called a type 2 error. We've made the wrong conclusion because we've said the foam roller type doesn't matter, save your money, don't buy the vibrating one, but in reality the vibrating foam roller does work. That's called a type 2 error. If in reality the treatment has no effect, but we think we see an effect, then that's an incorrect conclusion as well, and that's called a type 1 error. And then finally, if there really is a difference due to the treatment, and we find that there's a difference in our study, then again, we've made the correct conclusion. By setting our p-value, our alpha level at 0.05, we have a 95% chance, if we accept the hypothesis that the statistics support the hypothesis, that we're right. So by setting our p-value at a 0.5, we make sure that we have a 95% chance of making a correct conclusion. Okay, so that means every study that we read that has a 0.05 p-value, that means that 5% of them have made the wrong conclusion. So we have to keep that in mind. That's why it's important to see repetition of results. That's why it's helpful for us to see similar findings in multiple populations or multiple groups using slightly different techniques. If I see one study that says there's an effect and that the effect is real, I'm still very confident that what they found is accurate. It's 95% chance of being right. But if I see 3, 4, 5 studies that all show similar types of results, now I get more and more confident. So errors can occur even if the study is done completely correctly, because there's always that chance that, again, our measurements were somewhat off or something. All right, enough about statistics for now. We'll get back to some of these statistical concepts later if you're having some troubles understanding. But let's talk about evaluating the quality of experimental studies, right? We've talked about this over and over in regards to other types of studies and designs. If we find a study in a peer-reviewed journal, we can be fairly confident that they have followed high-quality design techniques, they've used the appropriate statistics, and so on when testing their hypothesis. But still, I think when we read these articles, we need to make sure that they're quality, but more so determine the applicability of the research to our research question or research interests. Okay, so I think it's important when we're reading these articles to keep an eye on the quality, make sure that they have used valid and reliable measures. Hopefully they've used a population that's similar to the population you work with. They've used testing devices or training apparatus that you have access to, and so on. So for the reader of research, I think more often determining quality is more so evaluating the applicability of the research to the things that you do or the things you're interested in. However, the concept of research validity is an important one. We talked about validity and reliability in response to measurement devices, measurement tools, but also when it comes to a study as a whole, there are important concepts related to validity. One of them is internal validity. Internal validity is the strength of causality. How confident can we be that the changes in the dependent variable are due to the treatment and not due to some outside influence? So in the foam roller study, for instance, if they were allowed to, if they wanted to, do stretching on their own, do other things, and the researcher didn't control for that, then that would mean the study doesn't have a lot of internal validity, because some things they did inside the time of the study could have actually affected the dependent variable. And therefore, we can't be as confident that the changes in the dependent variable were actually due to the treatment. They were due to some other activity that the person engaged in. External validity is the strength of the study in terms of its ability to be generalized to the population. So it's the degree to which the findings can be applied to other individuals or the individuals that you have an interest in. So that means we need to look at the study in terms of the characteristics of the subjects, the settings that they did the study in, that they conducted the study in, the timing of the measurements, and so on. So again, if I work with the elderly population that's looking to improve their strength, and I'm reading a study that evaluated strength in Olympic weightlifters, I certainly can get some information from that article that's of interest, but it doesn't have a lot of external validity because those individuals are very different physiologically, age-wise, performance-wise, activity-wise, than the population I'm hoping to apply it to. So the study may have great internal validity, but it doesn't have a lot of external validity. So those are concepts that we need to keep in mind when we're reading these studies and determining the quality and the applicability of that study to our own interests and needs. Here are a list of the references utilized in this creation of this presentation. Again, the book Research Literacy, A Primer for Understanding and Using Research was certainly a guide for the outline for this presentation. Feel free to take a look at that chapter in your book if you have it. And then obviously we utilized this research article as an example throughout this presentation.